Okay, now that we've done a couple of examples of the step 1 analyzing the function, step 2 analyzing the derivative, step 3 analyzing the second derivative and putting it all together, now we can jump into the textbook problems. I thought the textbook got a little too difficult, a little too quick. This example, our example 3, is the first example that they had in the textbook. And if you look in the textbook, it just says solution, and it gives you the answer to every single one of these questions with literally showing you none of the work. So all of this work has to be done behind the scenes to get any of the answers that they have in the book. So you cannot just give me what they have in the book. It will not count on the test. You have to show me all those works behind the scenes. So let's work through the example that's in the book where they just say solution and give you the answers. Let's work through every single one of those steps by hand and see how they got each one of those answers. Okay, so the first thing is the question of domain. The domain of a rational function is always, never factor and simplify first, always just set the bottom equal to 0. So that'd be x squared minus 4 equals 0. Add 4 to both sides, we'd have x squared equals 4. Remember, when you square root both sides, you have to remember plus or minus. So that'd be x equals negative 2 and 2. So really what we mean is x cannot equal these numbers. So here's the numbers negative 2 and 2, and we got to think about what can it be other than those numbers. It can be anything else. So what is the domain of this function? The domain of this function would be negative infinity to negative 2, negative 2 to 2, and then 2 to infinity. You do have to break it up. You cannot include those points, negative 2 and 2. So here's just a little foresight for you, a little insight into what the problem's going to do. If it's undefined at those points, then I know the derivative is undefined at those points, and I also know the second derivative is undefined at those points. So I know for sure when I do steps 2 and steps 3, or parts B and parts C, that I'm going to be breaking it up at negative 2 and 2. What I also know is I need to be really careful, because I might have a situation where my derivative goes from positive to negative at negative 2, and I might want to say, oh, that's a maximum because the first derivative goes from positive to negative, or increasing to decreasing. But it cannot be a maximum or a minimum because the function's not defined at those points. So when x equals negative 2 and 2, I'm always going to have my derivative and second derivative are undefined, but it can never be a maximum or a minimum, and it can never be an inflection point because it is not part of the domain. So be very careful with that, okay? Let's look at this. After we have already set the denominator equal to 0, the idea is try to factor and simplify the rational expression. Well, the top factors into 2 times x plus 3 times x minus 3, difference of squares. And the bottom factors into x plus 2, x minus 2. And that does not factor and simplify at all. So what can I do now? Now I can do my x-intercepts. An x-intercept is when the function equals 0. Well, the fraction only equals 0 when the numerator equals 0. So this would be 2 times x plus 3 times x minus 3 equals 0. We'll set each of those factors equal to 0. X plus 3 equals 0 gives me x equals negative 3. So that tells me the point negative 3, 0 is an x-intercept. X minus 3 equals 0 gives me x equals 3. So that tells me the point 3, 0 is also an x-intercept. So I have two x-intercepts, negative 3, 0, and 3, 0. We can also find our y-intercepts. Again, what is a y-intercept? A y-intercept occurs when x equals 0. Plug that into the function. It might even be easier into the original function here rather than the factored version. So that'd be 2 times 0 squared minus 9 all over 0 squared minus 4. Well, that's negative 9 times 2, which is negative 18 over a negative 4. So that's going to simplify into what? A positive 9 halves. So that tells me the point 0, 9 halves would be my y-intercept. Okay, so what do we have here? Now we can look at our vertical asymptotes and our horizontal asymptotes. If you remember, a vertical asymptote is once you have simplified your rational expression, you set the denominator equal to 0. Well, we've already factored it. And that's x plus 2 times x minus 2 equals 0. So x plus 2 equals 0 tells me that I have a vertical asymptote at x equals negative 2. And x minus 2 equals 0 tells me I have a vertical asymptote at x equals 2. Notice these are equations of lines, so I have to be very specific with this. I'm very careful with this. That I have to write them both as x equals and separate them. These are equations of lines. I do notice a typo in this. I should also have the horizontal asymptotes, because there is a horizontal asymptote on this problem. I should have that written down for you. For horizontal asymptotes, this is where it comes back to our section on the limits as x approaches infinity. That was called the in behavior, right? So what's our infinite limits? What is the limit as x approaches infinity and limit as x approaches negative infinity? And this is where you would look at it and you would say this function is balanced because the degree on the top is the same as the degree on the bottom. The leading coefficient on top would be 2x squared. The leading coefficient on bottom is just an x squared. So the x squareds would be simplify, and you would end up with y equals 2. So we do have a horizontal asymptote here at y equals 2. So this is lots of great information to help us finish analyzing the graph and also sketching the graph at the end. Those asymptotes are absolutely huge for us with our behavior. Okay? So there's our original function. Now we need to find the derivative of the original function and analyze that. This is not going to be fun. It's going to be a nasty quotient rule. But what I'm going to do is I'm going to write down the original function. I'm going to distribute the 2. So I'm actually going to write it as 2x squared minus 18 all over x squared minus 4. Now, that allows me to find the derivative using the quotient rule. I have to assume by now you're really good at finding derivatives, so finding the quotient rule or using the quotient rule shouldn't be too difficult for you. It's low, which is x squared minus 4, times the derivative of the high. Well, the derivative of 2x squared minus 18 would be a 4x, minus the high, which is 2x squared minus 18, times the derivative of the low. Well, the derivative of x squared minus 4 is simply 2x. All of that would be over x squared minus 4 quantity squared. I'm going to do some simplification here. I'll multiply out that 4x. 4x times x squared is 4x cubed. 4x times a negative 4 would be minus 16x. I'm going to distribute the negative and the 2x through to both of these terms. So negative 2x times 2x squared would be a minus 4x cubed. And negative 2x times a negative 18 would actually be a positive 36x. Put all of that over the bottom, which was x squared minus 4 quantity squared. Do a little more simplification. My 4x cubes cancel on top, and I'm ending up with negative 16x plus 36x. So I'm getting, what, 20x on top? And then on bottom, I'm getting x squared minus 4 quantity squared. That would be my first derivative of the function. Excellent. It's actually not as nasty as I thought it was going to be, but it is what it is. I need to look for my critical values, so that's when is the derivative equal to 0, and when is that derivative undefined. Well, the derivative is equal to 0, well, it's a fraction, and a fraction is equal to 0 when the numerator is equal to 0. So 20x equals 0 gives me x equals 0. That's my first critical value. And then I have x squared minus 4 quantity squared equals 0. Square root both sides, that would give me x squared minus 4 equals 0. Add 4 to both sides would give me x squared equals 4. Square root both sides, and I'd have x equals plus or minus 2. Okay, I want to be careful. This one right here, x equals 0, that is a critical value. X equals negative 2 and 2, if you remember, those are not in the domain of the original function. So technically, these are not critical values. They cannot be maxes or mins because they are not in the domain of my original function. So let's go back in here and let's create that number line. We have to break it up at all three places, negative 2, 0, and 2. Again, we're looking at the derivative at -2 and 2. It's undefined. And I know actually I'm just going to put this in while I'm thinking about it. My function is also undefined at those points. In fact, I know what it is. I'm not even going to say undefined. I know at that point it's a vertical asymptote. I figured that out in the first one, right? I look at my first interval, which is going to be -infinity to -2. My second interval, -2 to 0. Third interval is going to be 0 to 2. And my last interval is going to be 2 to infinity. I also know at the point 0, my derivative is 0. What do I do with this? I now need my sign chart. I need to plug it into the derivative. Again, the derivative being 20x all over x squared minus 4 quantity squared. Something that's less than -2, how about -10? In between -2 and 0, how about -1? In between 0 and 2, how about 1? And something that's bigger than 2, how about 10? I also look and I notice my denominator is squared, so no matter what I plug in, that denominator is going to yield a positive number. So let's look on the top. Plugging in -10 would give me a negative number. A negative divided by a positive is negative, so that entire interval has to be negative. Plugging in -1 again on top, I'd have a negative. A negative divided by a positive would also be a negative, so that entire interval is negative. Plugging in 1 on top, I'd have a positive. A positive over a positive is positive, so that entire interval, the derivative is positive. Plugging into 10, on top it would be a positive, so positive over a positive is positive, so that entire interval is positive. Any place that my function, where the derivative was negative, my function has to be decreasing. Any place where that function was positive, my function has to be increasing. If you notice at -2 and 2, the first derivative test wouldn't have said that it's a max or a min because it doesn't change sign. But if you do notice at x equals 0, we do know that because it goes from decreasing to increasing, that point must be a minimum. So let's actually find that point. Again, how do you find that point? You need to plug it back into the original function itself. So what was the original function itself? The original function itself was 2x squared minus 18 all over x squared minus 4. Again, I'm plugging in the x value of 0, but I've already done that. In all honesty, that's my y-intercept, right? So if I plug in the value x equals 0, I get -18 over -4, which we determined was 9/2. So that tells me that my y-intercept, 0, 9/2, that is a minimum. Okay? So let's go ahead and figure this out. Where's this function increasing? It's increasing anywhere its derivative was positive. That was in 2 separate intervals. We need to write it as such. 0 to 2 and 2 to infinity. You cannot say 0 to infinity. At x equals 2 it is undefined, so you can't say it's increasing at x equals 2. Decreasing was anywhere that derivative was negative. Again, that happened in 2 separate intervals. The intervals were -infinity to -2 and -2 to 0. Maximum, there was none in this problem. Minimum, we know that the minimum occurred at 0, 9/2. So there's our information right there from the first problems. We have our increasing, or from the first derivative, we have our intervals of increasing, decreasing, our maxes and our mins. Let's continue this problem and move on to analyzing the second derivative.